The broadcast is now starting. All attendees are in listen-only mode.
Hey, good afternoon, everybody, and this is Dr. Mansour. Sorry, I was trying to send some files. So some of you asked for some files, so I tried to send it. So this is the FE7. We are still in statics. Let us go over the material that I emailed it for those who attended before. For those who attended the first time, I would be glad to send it to you. Hopefully that I can finish the 9 chapters as soon as possible, and I can send the entire book. But basically, we are still in statics, and specifically under resultant in 2D. So the let me see if what the question here. Now, I believe you should be able to hear me right now. Okay, Badr, sorry, I was trying to send some material to your fellow engineers, those who are taking the exam this coming Saturday, Thursday and Friday, the PE. So if you look to this, I hope that all of you are on the same page. Resultant of two in the 2 dimensions, which is X and Y. So the equation that given in the NCEES, F is equal to the sum of Fx I from I1 to N if we have more than one component along the X direction, and square it, and the same story with the Y, and take the square root. So basically the resultant is given by this equation. So the resultant F of N forces with components in the X and Y direction has the following magnitude, and this is the language that's given in the NCEES. Now the angle theta, which is the, since the resultant is a force, so the force we need the magnitude and we need direction. So the direction is given by the angle theta, as we are going to see in the sample problem that will follow, is equal to arctan, which is tan minus 1, as all of you know, the sum of the Fy divided by the sum of the Fx. Okay, so this is the section that in the NCEES. The discussion I'm providing here is very brief discussion about resultant. What is meant by a resultant? Resultant is a force replacing series of forces, and we need to know its magnitude and its direction. So, for example, this sample problem 4.4, the 5 concurrent force systems, concurrent forces, okay, sorry, the concurrent system consists of 5 forces. They are acting at point A. The word concurrent is very important. If you remember, we talked about trusses before, and we said that the method of joints, we cannot pick a joint has more than 2 unknowns, because for any concurrent system, you'll find that sigma force X equals 0 and sigma force Y equals 0 are the only 2 equations available, because the moment equation has no value. So this is called a concurrent force system. I needed to remember this term, concurrent force system. Okay, so basically when we will talk about loads in the future, the 2 things that I mentioned before, I need you to remember that any force, let me start fresh here. I need you to remember this is FE7. I need you to remember that for any force or for forces in general, 2 important rules related to forces, and probably I mentioned them last time. Forces or loads in general, okay, these 2 rules. Number 1, any inclined force, inclined or slanted force, should be resolved into components. So any inclined force like this, I told you before that if this is the angle theta, or the slope is given in terms of horizontal and vertical, does not make any difference. So we need to get this f cosine theta, which is fx, and the fy is equal f sine theta. So we need to make sure that we resolve the given force or forces into the components. The second rule that we need to remember, and we're going to see this probably today in mechanics of materials, that any distributed load should be replaced with the equivalent concentrated load or loads. So these two rules, I need you to remember them very well, okay? So, like, for example, if you do have a simply supported beam, since I talked about an example of a slanted, or if I have a simply supported beam like this is a hinge, and this is a roller, and this is loaded with some kind of load. It could be uniform or non-uniform, but let's take it as a uniform load like this, a distributed, non-uniform load, where this here is W1 and this is W2 and this is L. In this case, it will be way easier to deal with this distributed load into concentrated loads. I will replace this with two loads. Each load will be acting at the centroid, okay? So we need to be aware of that. So let's go over this resultant problem here, problem 4-4. And okay, this is on page 5. Page 5 of the but from the sample problem, you should know what page you are in, okay? Page 4, page-4, but page 5, okay? Of the handout that is sent to you, to all of you statics, okay? So sample problem 4-4 or 4.4. So if you look to this, you will find that he's asking for the magnitude of the resultant force is most nearly. So we have a group of concurrent force systems. So in this case, this is a 2D. So this is X and this is Y. So this is already in the X direction. So it will stay as is. This in the Y direction will stay as is. But all these slanted force or this inclined force, they are going to be resolved, one in the X and one in the Y. And after that, I will collect terms and I will do the square root as indicated on the following page. If you go to the following page, which is page 6, by the way, just to make sure that everybody is following me. So this is a 2D concurrent force system. The two equilibrium equations, sigma force X and sigma force Y, will be used. And if you sum forces in the X direction, so the first force is already in the X direction, and the second force, which is 45. So let me go back again to show you one more time. So this is already, it will stay as is because it is in the X direction. This force is going to be resolved into two components, one in the X and one in the Y. The one in the X is equal 45 cosine theory. This one 60 cosine 60. And this one here, 90, will be cosine in the Y direction and sine in the X direction. And this is exactly what I did here. If you follow the solution, you will find that these are the components that, and we have to pay attention positive and negative, because this is a common mistake, okay? Because our coordinate system, as I mentioned, or as I joked with you last time, my grandfather and your grandfather agreed that these are the positive directions. So if you do have a force, like the force that it is here, the 90, so this has a component in the y direction, in the positive, but in the x direction, this has a component this way. So this is why you'll find this here is a minus. So the minus because it is in the opposite direction, as all of you know. The same story, I will follow the same concept. Excuse me. In the y direction, I collect all the terms, and we ended with, and after that I apply the equation that's given, which is this square plus this square, and take the square root, and here it is. And I wrote the two rules that I mentioned, and they are mentioned here, that any inclined force must be resolved into components, and any distributed load or force must be replaced with the equivalent concentrated load acting at the centroid. Here it is. So probably I could save 22 seconds by doing this. So so this is a straightforward problem, and you don't need to spend time by problem number 5, which is a following problem. Okay, if you look to problem 4.5, okay, is giving 3 concurrent force systems, 3 concurrent forces, also in 3 concurrent forces, A and B and C are given as shown. This is, and is asking the resultant direction with the X. And we need to pay attention because these 3 forces, these concurrent forces, will be replaced by one force, but I need only the direction. In order to get the direction, I will use the previous equation that's given in the NCEES, which is the theta, the angle theta. This will give us the direction. The resultant direction with respect to what? With respect to x. Pay attention to this. Okay? But this is the equation, but he could ask you what will be the direction with respect to y. Okay? So you have to be careful which angle he's looking for, because these forces will be replaced by, I have the x component like this, here it is, in the positive, and the y component is going to, components will be like this, which is in the positive. The resultant is going to be the closing, the triangle that this will close. So this is the resultant f, and this is the fx, and this is the fy. Obviously, this is the sum, and this is the sum. So this is the angle theta we're talking about, the angle theta. So if you look to the angle theta, you will find the angle theta is given by this equation. Inverse tan f sub y over f sub x, or the sum of all the components in the y direction divided by the sum of the all component in the x direction, and take the inverse tan and get an angle. Bingo, here it is. And the answer is A. And please let me know if you find a typo or a mistake or an error in the handout I received you. This is, you are the first group who see that, so probably if there is any typo or mistake or an error, please let me know, and I will be glad to take care of it. Okay, the second section that given in the NCEES is the resolution of a force. And now we're talking about the 3D. Okay, since we have X and Y and Z, so immediately I will look to the 3D system. So this is X, and this is Y, and this is Z. Okay, we have something called the right-hand rule. We're going to see it. When you rotate it from X to Y, you should advance in the Z. So if I decided to have my coordinates are different from what is shown here, if I call this is X and I call this is Y. So, okay, so when I advance from here to here, I have to advance to Z. So this is the right. So this according to the right-hand rule. You have a right-hand screw. Imagine that you have a screw and you're rotating the screw. Okay, so I'm rotating it from X to Y. The screw will advance, okay, in the Z direction. This will call it the right-hand rule. unless you have a screw that left hand, which is very rare that you will find that. Okay, so the f sub x and f sub y and f sub z. If we know the direction cosines, which is theta x and theta y and theta z, so basically the force is going to be basically fx is equal the force times the cosine, directional cosine, f cosine, f cosine. So the theta x and theta y and theta z must be given to you. Or sometimes we determine this, okay, by using this relationship. I can determine the angles, okay? You might be asked about to do that, knowing the components along each axis and the resultant component or the total force F, okay? Now, since we are talking about 3D, so the resultant right now is all the component in the x square, all the component in the y square, and all the component in the z square, okay? And also we can use this expression, which is basically the same thing. Instead of cosine, the cosine is x over r, y over r, and z over r, where r is the resultant, okay? Problem 4.6, he gave you a 3D system, x, y, z, and he gave you three forces, F1, F2, F3. And is asking if we need to find the resultant, if we need to replace these three forces by one single force, okay? Which one of these diagrams will be representing the resultant? So basically, I took the three forces and we add them. So if you add the I components, so 15 and 20 minus 10 will give you 25i. Same story with the j and the same story with the k. So the diagram that has 25i, 60j, and 55k is the correct one. If you look to this, so you'll find that the diagram A is the correct one. Is this correct? Yeah. Diagram A. Okay, they agreed, by the way, or this is XYZ. So the unit vector along the X direction is I, and the unit vector along the Y is J, and the unit vector along the Z is called K. So I and J and K are unit vectors. Okay, it has a magnitude of 1. Okay, we call them unit vectors. Okay. If you flip the page, you will find that moment. Okay, moments or couples. Moments, by the way, it could be for a 2D or 3D. Okay, moment, and we're going to see both. So we're talking about moments or couples. In case of 2D, which is two-dimensional, so the moment is equal force times distance, F times D, where D, we call it the moment arm, and F is the force. So if I do have a force like this, F, okay, and I have a point O, and I need to find the moment of this force about O, I must find the arm, which is D. And the arm must be perpendicular to the direction of the force. And this, it could be either clockwise or counterclockwise or CCW. So this is an easy for 2D. It is just force time distance, and we're going to see some examples shortly. But for a 3D, the situation is a little bit different. So the moment as a vector is equal R as a vector, a cross product F. Obviously, M is a bold face, R is a bold face, and F is bold face. The textbooks, they use the bold face as a vector, a quantity. Like, okay, I needed to pay attention to that, okay? So the a system of two forces that are equal magnitude and opposite in direction and parallel to each other is called a couple. Okay, so in this case, if I have a force, this is F, and this is F, equal magnitude, opposite direction, and they are separated by a distance, D, for example, I can replace these two forces, okay, by a moment or a couple where this is F times D. And obviously, as you can see here, they are rotating counterclockwise because of the direction of the forces. This is what is meant here. Okay, in the 3D, we are talking about the moment as a vector quantity is equal R times F. This R is not the radius. It's called radius vector. It's not the radius of a shaft, as we're going to see it later on. So I need you to know that. As far as the scalar quantity, this is a vector quantity, this is scalar. Scalar quantities. I can find the magnitude of this moment about the x-axis, about the y-axis, and about the z-axis as given by this equation. But this is the equation. And since we are multiplying R times F as given, this here we call it a cross product. Cross product. There is a dot product and a cross product. Dot product means that there is a dot in between, and we're going to see this later on. But for the cross product, like this one here, okay, so it is vector cross product. I need you to remember, if you forget the sign and the direction, most of the textbooks, they are saying that I, J, K like this in the clockwise direction. If you multiply I cross J will give you K. J cross K will give you I. If you multiply K cross J will give you negative I. Okay, so if you are going in this direction, this is a plus. If you are reverse it, you are going to get a negative sign. Okay, so if you look to this, you will find that, first of all, I need you to know that I times I, J times J, all this cross product, obviously K cross product K is equal 0. Okay, the I times J, which is, this will give you a positive K, or negative J times I will give you this. So I need to remember, this is not given in the, or maybe given in the math section. I can't remember if it is given in the math section, but this is just to illustrate to you the, so the moment as a vector quantity is equal R times F, where R is a position vector or the radius vector, as we call it, radius vector or position vector. So we are talking about the moment is equal, if I have a force F, and I need to find the moment. Okay, so I can select a position vector, which is R, by selecting any point along the line of action of the force. And I need to find the moment about A. So the moment about A, as indicated here, is equal the position vector Q with respect to A times F. Or if I decided to select another point, like point B as in boy, so B with respect, this is how we write it, okay? Position vector R, B with respect to A. Okay? And the direction, by the way, because vectors, I am directing it from A to B. As you can see, this arrow is going this way, or from A to Q. Don't reverse it. If you from Q to A, you will get wrong answer. And this is just to illustrate the X, Y, Z. And the same three equations given here, I repeat them here, mx, my, and mz. Okay? So 3D is a little bit difficult, but we need to be familiar with it just in case. This is to illustrate two forces equal magnitude opposite. So, but don't forget that the arm it should be the perpendicular distance between the force and the point, or between the two forces. In this case, if I have two forces, equal magnitude, opposite direction. Okay. Problem 4.7. I hope that you have the same copy. It seems that the only copy left here with me is the copy that it was shifted, so I corrected. So it seems to me this is the one I'm using, and I hope that all of you have the corrected one. If you look to this bracket here, or this angle here, or an angle bracket, is subjected to forces and couple as shown. So I have a couple here, I have a force here, I have a force here, and I have a force here. And the dimensions are given as shown. And the question is, the equivalent force couple system at point A is. So if I'm going to replace the whole system to be one force and couple, what should I get, or what should be the value? So when you sum moment about A of all these forces, I need you to remember this is a slanted force or inclined force. So in this case, I have to replace it with two forces, one parallel and one perpendicular. So right now, this one here, 150, I divide by 5. What's this 5? The 5 is the hypotenuse. 3 square plus 4 square. And I need the vertical one, so I multiply by 4. This, in fact, is a cosine. Okay, the x component is going to be the 150 divided by the hypotenuse, which is 5, times the vertical one, or the horizontal. In this case, the horizontal is 3, already the vertical I did. So this is gone. The beauty about resolving forces into components, one in the x and one in the y and one in the x, when you sum moment about A, will be much easier for you. Way easier, because I know the distance, which is this here. But if you leave the force as is, the moment basically is the force time distance, so I need to get the arm. How can I get this D, which is sometimes difficult and time consuming? So generally speaking, it is better to resolve all the inclined forces into components. So as you can see here, the first number is the resultant, R, and this is the direction of the resultant, which is angle theta, and we have the moment, which is M. Okay, this, as you can see, this is an easy one, because this is what? This is X and Y, so this is a 2D system. So if you flip the page, you will find all this. Okay, so I will sum all the forces in the X direction, all the components of all forces in the X direction. I ended with this. Sum forces in the Y direction. Again, as you can see, we divide by 5, we divide by 5, and we multiply by the appropriate dimension in the X or the Y, as I indicated to you. So here it is. So the resultant, it is a sum square, and take the square root. Here it is. The angle theta. Now we need to get the equivalent moment. And since he mentioned the word in the problem statement, the point A is my point that he, so I am putting my finger here, and I am summing moment of all forces around point A. So this is 200 Newton times this dimension. I have 150 times this dimension. These two forces here, the X component has no moment because it has no arm, but the Y component has an arm of 15. But when you come to this moment here, moment or couple is acceptable. He said that a couple, okay. This already moment. So you transfer the moment, because the moment is a free vector, will transfer at any point along the beam or along the section with its magnitude and its direction as given. So I don't multiply the moment by another distance, because already here it is Newton meter. So don't do mistake and say that, oh, I'm going to multiply this by this distance here. No, we don't multiply the moment. So this is why you find that the 50 Newton meter as is. No distance, it's already moment. But all other forces, you will find there is an arm, there is an arm, there is an arm. I need you to be aware of that. And when you sum moment, when I say sigma moment about A equals 0, which is one of the equilibrium equations, as all of us know, you have the choice to assume clockwise positive or counterclockwise positive. It's up to you. This is optional, as I mentioned last time. Okay, so it is, I found a moment and go over it and let me know. The following section is talking about, this is what you will see on the exam, the information that's given in the NCEES formula book, which I hope that all of you get a chance to download it, or you already, the NCEES reference book, the one I showed you a couple of times, NCEES reference book 10.0. So here we're talking about, again, you'll find that the boldface, that means that we're talking about the 3D. The force is equal to the sum of all the forces, okay, and the moment is the sum of all the moments, and this is a cross product vector, okay, position vector time. I talked about that here, I explained all these things, and you'll find for a 2D system we have 3 equilibrium equations, which is sigma force x, sigma force y, and sigma moment. But for a 3D we have 6 of them, so those are 6 equations, and we have only 3 equations here for a 2D system. Here I gave you some additional information about the forces, okay. This we call it a 2-force member, like a truss member. Also it could be a 2-force member where you have 1 force here and 1 force here, okay. This is the 3 force. They are concurrent, they are meeting at a common point, and this is a parallel system. This is a non-concurrent, this is a concurrent force system. So I needed to be aware of that, just in case if they mention. I illustrated also the 3D to give you some information about the 3D for free body diagram like this, okay. And this can be translated like this in the X and Y and the Z. If you have a 2D system, free body diagram, a cantilever beam carrying a distributed load. This distributed load, as you can see, I replace it with W times L, because this is L as indicated here. So this is the total load, and this will be acting at the centroid. The centroid is L over 2 and L over 2 from each end, as all of us know. So free body diagrams, basically you are translating the given information into a simplified diagram describing all the forces that's given, or all the forces that are given. Types of supports, we need to know that. A hinge, it has only 2 unknowns. A roller support, it has only 1 unknown or 1 reaction, and it must be perpendicular to the contact surface. As you can see, I draw the perpendicular here. A fixed end, like this. Fixed end, this has 3 components. Here, I didn't show, okay, the horizontal, it should be H, because it's a 0 in our case, because I have this in the y direction. So I have V is equal P in this case, plus WL over 2, or WL, sorry, in this case, okay? And the moment, which is called the fixed end moment, which if you sum moment, you will get the moment is equal P times L plus WL times L over 2, which is WL squared divided by 2. And we are going to solve some problem like that. So I need it to be, so the fixed end, it does have 3 unknowns. Even if they are, one of them is 0, still we are showing that because you are using the 3 equations. And the last one is called a link, like a truss member. Okay, it does have only one, okay, force, either tension or compression. The line of action is along this link. Okay, it's one unknown. Here we have three unknowns. I needed to remember that, three unknowns. Because when you look to the problem, you need to decide exactly how many unknowns and what will be the appropriate equation to. Okay, let us look to this problem. This is a system. I have two cables and supported or are carrying the 700 Newton as shown. And he would like to find the tension. So this member is going to be, or this cable has a tension, FAC, and this member here, it has FAB. So two unknowns. This is a concurrent force system. So I draw a free body diagram of this joint A, and I have two equations, sigma force X, sigma force Y. Two equations, two unknowns, because I have only two unknowns. Solving these equations simultaneously, you will get the two unknowns. So this is if you decided to use the resolving the forces, one in X and one in Y. And we need to know that. You see here also 3, 4, 5 and 45 degrees. We need to make sure that we are using the proper sign. There is another way we can do it, is we can construct what is known as the force diagram. The force diagram. And the force diagram, basically, I constructed based on the given. So this force diagram is coming from the given information. I know 700 down, here is 700 down, and I have tension along AC is going this way, and the tension along AB is going this way, close it. And if I can find the angles, which I can, based on the given information, he should give you enough information, I can use what is known as the law of sines. The law of sines and the law of cosines are given, okay, in the math section, by the way. I believe A is mentioned in the math, and we need to remember them. So it is A over sine the angle A, B over sine of the angle B, and C. So let me do this. Okay, at least you can remember that. So the law of sines and law of cosines are very important. Yeah, it is in the math section. Yes, I just saw it. Here it is, math section under a trig. Okay. So if you do have a triangle like this, okay, and let me use the same notation they are using. If this is A, and this is A, and this is B as in boy, and this is B, and this is C, and this is lowercase c. So basically, if I have this triangle, so in this case, I can say that this side here, or this starts with A over the sine of the angle, the opposite angle to this side, which is angle A, is equal to B as in boy, divided by the sine of the angle B, and finally C over sine C. This is called the law of sines. The law of cosines, we're saying that this dimension square, let's start with A square. A square is equal B square plus C square and the minus 2. These two sides, which is B times C, times cosine the angle A in between. So A square is equal B square plus C square minus 2 times the two sides times the cosine of the angle in between these two sides. And you can repeat the same thing, B square and C square, and I give it to you. So this is a repetition. Here it is. And you should know this very quickly, and you will see, we'll see it again on the math. So in this case, after I construct this, I can use the law of sine, and I can determine the same, the 500, I get the same 500, and this is here. So you have the choice either to use the two equilibrium equations, sigma force X and sigma force Y, and solve the two unknowns. Or if you decided to use the triangular force and use the law of sines. All these things are very important. If you look to this problem here, problem 4.9, a 2D frame subject to 4 forces and a moment as given. So I have a force here, and a force here, and a force here, and a force here. During the exam, by the way, common mistake that sometimes if there are too many forces, sometimes we may forget one. We need to make sure that we consider all the forces. In addition to that, he's giving you a moment. And a moment are given. And he gave you a statement here. Okay, if the frame shown is bent so that it rotates about point B, the counteracting moment that must be applied at point A, where the location of the 200 Newton, to put the frame in equilibrium is most nearly. Again, this is the moment equation, and I am reminding you again with solving the forces. If you have any force that should be resolved into components, do that. Like this one here, and you are going to see this one will sum them. So I am summing moment about this is B, by the way, this is a B as in boy. This is what he's talking about. So if I sum moment about B as in boy, I put my finger here, and I need to assume a direction. Which one is a positive? I assumed in this time, counterclockwise to be positive. I assume that. It's up to you. Okay? So this here is given moment in the clockwise direction, 700 Newton meter. But my assumption, this is positive. So this is why I put a negative sign here. And after that, all the forces, this is 150. 150 times 4, here it is, 150 times 4. This is already in the y direction, so there is no need to resolve this. But this 150 here, this one here, does this force has a moment about B? No, this has no moment because, so I have 1, I have 2 here. This here, it has 2, 1 in the x and 1 in the y. And this has 1 in the x and y. So 2 and 2 is 4, and 5 and 6. So I must have 6 terms. 1, 2, 3, 4. I missed something here. Oh, yeah, I'm sorry. I did a mistake. Okay. Yeah. This is in the x direction, and this is in the y direction. Okay. This is the y direction, and this is the x direction. Okay. So which force or what forces does not have a moment? This is why I said that let's count, because this is a common mistake. So this one already moment about B, so it will show up. This has a moment, yes. This one, no. This one, the x component, yes. And this is yes. So I will say yes and no. At least we can count how many yes and how many no. And this is yes. Okay. So this one here, yes. This one here, no. This is why. So let's count how many yes. 1, 2, 3, 4, 5. So we ended with 5 terms. 1, 2, 3, 4, 5. The mistake I did very quick when I was saying that this is 6. Okay, no, this is in the y component, so it does have no moment about point B. Okay, so please do this, because this is, again, it could be a common mistake that we do, that we ignore one force, or we did not consider one force. This is a very common mistake. And the point, for example, this force here, What is the moment of this force about this point O? 0. M about O is equal 0. Because there is no R, exactly like this. This Y component goes through this. And the same story, the 150, it goes through this. So these two, they have no moment about point P because they don't have an arm. And this is what. Okay. The second section here is talking about centroids of masses, areas, lengths, and volumes. They give us series of equations. And here what you will see, centroid or centroids for all these things. So basically, if you do have a mass or you have an area, there is one location here, we call it the centroid. Okay? And we need to locate this centroid for any given area or given mass or any given volume. The equations are essentially the same, except one time we are using the L for the length, one time we are using the mass, and one time we are using the area. So all these equations are given to you, okay, on the exam. And here, this is the an area, for example, here, and it has a centroid, and the distance from the centroid to the x-axis, we call it y prime, and this is x prime. Okay, they are using, by the way, the saying that XAC, which is this equation here, which is the sum of the xn times an over the sum of the a, and YAC and XAC, by the way, this is the one sometimes we use it as a x prime and y prime, which is the distance from the centroid to the reference axis, Like, let me give you a problem that we covered it in the seismic design, and we covered it in this PE. If you do have an angle like this, T, let's make it T much easier. T beam. Let me make sure that I have a nice T for you. Okay. So let's assume this is 8 inches. And here 2 inches. And let us assume that this from here to here is about 6 inches. And assume that the web thickness is also 2 inches. Okay. So this area has a centroid C here. The distance from here to here, this is what we call it the YAC. But in the NCAAS, they call it YAC. Okay, let's stick with the. So basically, this, as all of you know, this is a flange, and this is the web. So to get the YAC, I will use the equation given in the NCAAS. YAC is equal, here it is. The sum, you don't have to memorize the equation. The sum of the YN AN divided by the area. Area is the total area of the given section. But lowercase a n, that these individual areas. So in this case, I will divide this into 2 sections. The flange and the web. So I will take the first one. This is a flange. It has a centroid. Okay. And as you can see, I use this as my reference. So from the centroid of the flange to the reference line is what? 6 plus 1 times its area. What's the area? It is 8 times 2. So I finish the flange. Plus, I will look to the web. What's the distance from the centroid of the web to the reference line? This is 6 inches. It is halfway, so it's 3 inches. All these are in inches, by the way. Times its area, which is 2 times 6. Divided by this total area, which is 8 times 2. a plus 6 times 2. This is the way we do it. So it is 7, if we'd like to do it to get some numerical values. So it is 7, enter, 8 times 2 times 112, a plus 3, enter, 6 times 2 times, which is 36. Sometimes we don't need to do 36, divided by the 2 times 8 is 16, and this is 12. So the total here is 28, and 112 and 36 plus and 28 divided will give us 5.29 inches if we round it. That means that the centroid of this given area is located at a distance YAC, which is 5, a little bit below the flange. Why we need to determine the centroid? Why? What is the benefit for us, or why we, as engineers, we are interested to locate the centroid? Because the two axes going through here is called XC, and this is YC. At the end of this section of this chapter, I provided you with the tables that you will see it in the NCAAS. Okay, if you jump all the way to the end on page 40, you will find that these tables are produced from the same document. Okay, and you will find that for all these different areas, they are using the XC and the YC. They showed you where is the centroid is, and they are saying that how much is the XC and how much is the YC. Obviously, from here to here, this is XC, and from here to here is the YC. And after that, you will find that this is easy stuff, the area and the centroid. If you go to the second column, you will find that we have IX, IY, but also you'll find that IXC and IYC. So the X and the Y as shown, and the XC and YC like this. This is the XC. I don't know why they didn't put it, unless they put it. Okay, and this is YC. So the XC and YC, we call them centroidal axes, or the axes, the two axes, they go through the centroid. This way you'll find under the moment of inertia for the area, you have two values, one under the XC and YC, and one under IX and IY. You have to be careful about that. And the same story with the radius of gyration. The RX, RY, and the RXC and the RYC, as we're going to see. And after that, we have something called a product of inertia, which is IXY or IXC and IYC. So for any given area, okay, I could assign this is X and this is Y. So I can say that these are the two axes, X and Y, but they are not the centroidal axes. I can say this is the X and this is the Y. But the two centroidal axes, they have to go through the centroid, XC and YC. And later on, when we'll come to the chapter, which is the next chapter, Mechanics of Materials, when we're talking about sigma is equal MC over I. The bending stress or flexure stress, very important equation, we're going to see it. Flexure stress or bending stress. This C is a distance. Distance measured from where? From the centroid to the up or to the bottom of the section. This way, this here, for example, we have C top and C bottom because it's not symmetrical section. C bottom. But the point I would like to make here is the distance C is measured from the centroidal axis. Okay, you have to be careful because we need to know what is the moment of inertia and what is the radius of gyration and the product moment of inertia, and we're going to see this. Okay, so the going back to the sorry, I'm trying to go a little bit fast and try to finish as much as I can today. So if you go back again to the section of the moment of inertia, you'll find problem 410. Problem 410 on page 16, based on the, this is a given area, okay? And he's asking what are the X and Y coordinates of the centroid. So I'm using the composite area technique or the composite area method exactly as I used here. This is called the composite area because I am taking each area individually and multiplied by its own distance divided by the total area, which is, so this is called the composite area. So the composite, if the word composite is mentioned on the exam, the composite area method is what we are talking about here. So if you look to this, divide the given area into common areas like square, rectangle, triangle, and so on. As you can see, I divided to 3. 1, 2, 3. Because it's easy to deal with common shapes. Easy one and straightforward, and you can do it with minimum errors or minimum mistakes. So I have area 1, area 2, and area 3. For each area, for example, area 1, this is 5 centimeters, and this is 2. So 5 times 2 is. Where is the centroid for this? The centroid here in the middle. So I will call it C1, for example. C1. So this, the distance from here, this is called XC. So the XC is half of the 2 centimeters, which is 1. And this is 5, is half, so 2.5. And the same story with this. C2. And C3. C3 is a little bit difficult because right now this is a triangle 1/3 and 2/3. You have to know exactly how we do this. And here it is. So I defined the area. After that, it's just a matter of applying the equation, or the equations in this case. And you ended with 2 numbers. And it should match one of these answers. So composite area method, the composite area for centroid. Centroid. The word composite will be shown again, by the way. I don't like you to mix between composite area and composite materials. Composite materials, we're going to see it later on in the mechanics of materials. Okay, I left it, even they dropped it, but I left it as the composite, which when we have 2 different materials, and we are going to see it later on. Let me wait until we hit it. Let's take a few minutes break and come back. I need to take a short break. I was teaching, and I will before that, and let's take a few minutes break. Right now is about 5:35. So stretch your back and get some fresh air. As I always joke with you guys, air without corona, please, because we don't like to have any corona, because corona is not good. Okay. Hopefully we can wrap up this as much as we can, because too much material, but we will do it. We will do it. Okay, we will do it. So let's take a few minutes break and come back. Right now is about 5:35, so 10 minutes from now, so it will be 5:45, please. Thank you. Hey, welcome back, everybody. Another sample problem related to the centroid. So you given this angle shape and all the dimensions are given, and he's asking the centroid of this area is located, and they give you the x and y. And in this case, he defined this is x and this is a y. So the centroid somewhere here, and this is the y, the y AC, and this is the XAC. Okay. Again, we are going to divide the area. It's up to you. You can divide this way or this way. This is the way it is done here, area 1 and area 2, and the XC and YC again. By the way, this is a moment of the area about the Y, and this is a moment of the area about the X. And the moment for the area is equal, basically, the distance times the area. So this is the expression that we need to be familiar with. And we got an answer like this. So the XA is 3 and YA is 2. Sometimes, by the way, because of the time, you will be given 110 questions, as all of you know, for the questions. And you have 5.5 hours. So basically the time is the biggest enemy for you. So sometimes that you can use your, if you solve for the XAC first, you'll find 3. So and if you are really sure about your calculation, and we are lucky, the only XC is equal 3. So there is no need to compute the other one. Okay, but sometimes on the exam, for example, if this distance XAC came 2, I have 2 answers, they having the same, okay, number. So in this case, you have to solve for the other in order to get. So he could make my life difficult by putting, okay, this is 3 and make this 1.5, for example. So in this case, after you calculate the XC or XAC, you get the X dimension. In this case, you are narrowing the choices between answer C and answer D. But here we are lucky, we have only one answer that matching this. I can pick it up and go home happy. And okay, the centroid for volume or for length, it could be computed also. This is a centroid for volume. So you have the following structure: 3 solid aluminum rods, and each one is 1 centimeter in diameter. So for the volume, sorry, the camera froze for some reason. Yeah, here we go. Okay, so the x coordinate of the centroid of the volume, so the XC is equal the sum of the X volume total the volume. So what is the volume? And we're going to see this, by the way, we'll talk about earthwork. Okay, volume, we're going to see this in surveying, and we're going to see this in transportation. Volume is equal the area or the cross-sectional area times length or times depth. Okay, area times depth. For the PE, we have more than one method. For the FE, they give you only 2 methods. One is called the average end area, and the Prismodial method, and also they include the prism or the prism or the pyramid, like the Egyptian pyramid. Okay, so we're going to see these methods later on in another section. But all of them, they came from this basic equation that we learned in high school. The volume is equal to the cross-sectional area times the depth or times the length. So here, the volume is equal to by d square over 4. This is a cross-sectional area. By d square over 4 times the length, because each member has. So we calculate volume 1, volume 2, and volume 3. And after that, we apply the equation. And each one is a centroid in the middle. For example, here, okay, you will find that the first one, which is 6 by, this is, okay, which is this one probably here. So take the center from here, centroid from here, centroid from here, and measure. And substitute, not measure, so substitute for the value of each. And we ended with this number. So the centroid is subject that you might see on the exam. The following one is called moment of inertia. Moment of inertia is, some books, they don't like the word inertia. They call it the second moment of area. Moment of area. And you may say that, why we call it second? That means that we have a first? Yes, we have a first moment of area. We're going to see it. It's called Q. Okay, so the moment of inertia, let's stick with the name that's given in the NCAAS, okay, or the second moment of area, oh my God, here it is defined as, so it could be either one of them, but the moment of inertia was italics like this, is equal to Ix and Iy. So if you have given any area, and this is X and this is Y, and you do have an area, so we need to get the moment of inertia about the X and Y. They are given by both. We have something else is called polar moment of inertia, which we call it J. We are going to see an equation, theta in the mechanics of material is equal TL divided by GJ, or JG, sorry. Let me put them in order, JG. J is a polar moment of inertia. G is called shear modulus, something different. But J is the sum of the Ix plus Iy. It's called polar moment of inertia. Okay, which is the R distance, R polar, which is the radius of gyration. Okay, so, and we're going to see this, all this polar moment of inertia and radius of gyration and all these things. So, moment of inertia is, as I describe it here, I'm using the same notations. The moment of inertia, which is, and the J, which is the polar moment of inertia, we need to know that. It is the sum of the Ix plus Iy. And the table that I was talking about, by the way, or the one I was discussing when I mentioned the XC and YC, they have some the expressions for the moment of inertia for common shapes. Okay, and we're going to use it. I have a problem number 13. Two circular areas are given, and it does have, each one has a radius of 4 meters. The polar moment of inertia about the composite, okay, centroid, is most nearly. We are going to see an equation, it's called the Parallex Axis Theorem, which is very important. Parallex Axis Theorem, I believe I do have a, yeah, it's coming. So the Parallex Axis Theorem is given by this equation. So I can use the Parallex Axis Theorem in order to get the polar moment of inertia. Okay, by the IXC. If you have a circle, the circle has a centroid. This is called XC, and this is called the YC. The NCEE is using the letter A for the radius. I will take you and show it you right now. So the moment of inertia, the IXC, is equal pi a to the fourth divided by 4. You don't have to memorize and you don't have to derive any equations. Let me take you to the two tables I was talking about and show you the circle. And they have, so table is, this is the second page of the table. It is in my book on this chapter on page 41. So this is a circle, and they use the letter A, by the way, for the radius instead of R, because we are using R for the radius of gyration. So they will not, so they don't like to confuse us. So what is this is a circular area. It has a centroid in the middle, and the letter A is the half of the diameter. So the area is given. If you look to the IXC and YIC, here it is. This is a pi a to the fourth divided by 4. So this is the because where is XC and YC? Here it is XC and YC. So the XC and YC are the two axes. They go through the centroid. Okay, and they are equal in this case. Okay, this is why you will find that for bridges, we prefer as engineers, and you will see this later on, for columns, for the columns of bridges, we prefer circular columns. Circular columns. Okay, why? Because if you look to a circle, you find that this is XC and this is a YC. And the IXC is equal to IYC, which is equal to pi a to the fourth divided by 4. We are going to see one equation in mechanics of materials. It's called buckling a critical load, or P critical. Buckling. Buckling is a serious issue for columns. If you have a column, and this column is subjected to axial load, so if you increase the load from column at one position or at one load value, it will buckle like this. It's called buckling. It's called buckling. And buckling is one of the failure modes. We're going to see buckling. One professor, his name is Euler. Okay, he is a Swiss mathematician. He came up with the Euler buckling formula, and we're going to see it is pi square EI divided by KL square. This equation, we're going to see it in mechanics of materials. It's called Euler's buckling formula. And they came up with another equation. It's called sigma critical, which is the pi square E divided by KL over R square. This is another equation. We're going to see it. It's called the critical stress, critical buckling stress. R is the radius of gyration. Radius of gyration. So when we design columns, circular columns, the IXC is equal to IYC. And also you'll find that the RXC is equal to RYC. The radius of gyration, they are essentially the same. Here it is. The R and the R, it is A squared over 4. So the probability of buckling about the x-axis or the y-axis is the same. So to eliminate the human error, because if this column is a rectangular column like this, a rectangular column, but sometimes you will find that this is x and this is y. You will find that the Rx is not the same as Ry. So if I did a mistake in my calculations, maybe I will be in big trouble because I might have failure because of the human error. So in order to avoid that, so we prefer the circular columns And there's another reason for that we'll talk about later on when we talk about design. But this is something that I need you to be aware of. So we do have the Rx and the Ry and radius of gyration, and we have the there is one equation is called the parallel axis theorem. We're going to see it, and it's very important theorem. We need to be aware of it. Let me go back again to the sample problem that I was talking about. This is a problem 4-13. So I know by a to the 4, this is from the table. The table, okay, at the end of this, oops, let me move my camera here. Table at the end of statics section. And you need to be familiar with these tables because we need to pick the right value very quick. So I applied the parallel axis theorem. Why? Because the moment of inertia is here about its own centroid, the XC and YC. And the same story for the other one, XC, but he needs it to be here. Okay, so I have to use what is known as the parallel axis theorem, and I will talk about the parallel axis theorem on the following section. And very interesting theorem, and we need to be aware of it. The parallel axis theorem is very, very important, and I need you to be familiar with it. And it's given here. Moment of inertia, parallel axis theorem. They are using this illustration, and they are using this equation. This is a centroid, and this is, he call it X prime and Y prime. Unfortunately, they are using also, no, this is supposed to be XC and YC to be consistent, but they call it X prime, Y prime. The two centroidal axes. They took this from another book, from Hebler. Those of you who took the class statics, they know Hebler. So this is a given area. And I know the centroid, or I know the location of the centroid, and the two axes that they go through this is called XC and YC. If I need the moment of inertia about IX or IY, I don't know, this drawing, I see something, okay, it doesn't match the equation, but I will look at it, I'll review it. The IXC and the IYC, these are the moment of inertia about the centroidal axis. Here it is, centroidal axis. And IX prime and IY prime, this is a moment of inertia about a new axis. And the d sub x and d sub y, dx and dy, are the distance between the two parallel axes. So basically, they are telling us in the parallel axis theorem that I do have an area, and let me derive it for you in one of the sections that's given in the table. A rectangular section is very easy, and the rectangular section let me see what they use for dimensions to be consistent with them. They are using H and B and H. So the H is the depth and B is the width. So if you have a rectangular section like this, and this is H, the centroid in the middle by inspection. So, and this is the XC and this is YC. You will find that the IXC is equal BH cubed over 12. So the IXC is equal B H cubed over by 12. If I do have another X like this X, I need to find the moment of inertia about IX. This X is here, X is parallel to this one. So if I apply the parallel axis theorem, so IX is equal to IXC plus A D, this is the dy square. So let me do it. IXC is given as BH cubed divided by 12 plus. What is the area of this? The area is very easy. It is B times H. Times, what is dy? This is a dy. How much this dy is H over 2. And this is square. If you simplify this expression, you will find this is BH cubed divided by 12 plus BH cubed divided by 4. You multiply here 3 and 3. So this will give you BH cubed divided by 3. So I have two numbers, and you will see them in the NCEES, the BH cubed divided by 3 and BH cubed divided by 12. But we need to know which one is which. Let's look to the NCEES. This is the table that I'm referring, which is on page 40. And this is the rectangular shape I'm talking about. You will find that the IXC, I use only IXC, is equal BH cubed over 12. Here it is. But if you look to the IX, you will find is BH cubed divided by what? 3. There is a huge difference between these two. This is a moment of inertia BH cubed divided by 12. This is the two axes going through the centroid. But this is the x-axis here, which is parallel to the centroid. So the two numbers I need you to be aware of, because you need to know exactly what they are asking for. So this is called the parallel axis theorem. The parallel axis theorem, there are two requirements. I put them at the bottom of the equation that's given. I put them here. I am on page 20. Applying parallel axis theorem requires, two conditions or two requirements. Number one, the two axes must be parallel. Must be. And one of the two axes must be the centroidal axis. So those two requirements are very, very important. Okay? So the two axes must be parallel, and one of them must be the principal of the centroidal axis. This problem was given, by the way, in one of the FE book way back, actual exam book. They release it from time to time. So sometimes I pick this problem, problem 14. The area shown is given. It is 6,000 millimeters square. The distance between the centroid of the area, the centroid is here. This is C. And the line AA is given to be 100 millimeter. And the moment of inertia about the line AA is given. So the IAA is given to be 63 times 10 to the 6. And is asking, what will be the moment of inertia about line BB? So this problem is so tricky. I cannot apply the parallel axis theorem between this and this. No, I cannot. Because neither is the centroidal axis. The centroidal axis here. So this is XC. I can transfer from here to here, yes. But from here to here, no. I cannot do that. So first, I need to determine what is the IXC. And after that, so here it is. So I use the equation that's given. This is given, and don't know the IXC. I get the IXC, then this is step number 1. Step number 2, since I know the XC right now, the IXC is given to be 3 times 10 to the 6 millimeter to the 4th, by the way. Units are very important. In this case, I can apply the parallel axis theorem. We'll say that the moment of inertia about this axis, which is IBB, is equal to IXC plus the A or the dy square A or A dy square. So we need to be aware of that. This is a very good problem, and in order to understand the parallel axis theorem, problem number 14, please pay attention to this problem. Okay, radius of gyration is a property. We have Rx and Ry, okay, and Rb, which is a polar radius of gyration, and these are given like this. Rx is equal to the square root of Ix over A, and Ry is equal to square root of Iy over A, and the R sub B, which is J. Do you remember J? J is a polar moment of inertia. Polar moment of inertia. Nobody will ask you to memorize these things, but by practicing and practicing, you will be able to recognize some of them. For example, I use the same 2 circular areas that given before. What is the polar moment of inertia? If I know J and I know A, I can get it and take the square root because it's given by this equation here directly, and this is straightforward. Okay, we have something called the product moment of inertia. We call it IXY, the product of inertia. Is given by, if I need to start from scratch, the integration. And also I can apply the parallel axis theorem, by the way. So, and this is the equation that is given here. I repeat it again with a little bit of explanation. I need you to remember something very, very important, that if one of the axes of the reference axis is an axis of symmetry, so the product of inertia is going to be 0. So for example, if you look to this, X and Y, for a rectangular section like this, the X-axis, this is H, and this is B as in boy, the one. So the X-axis is an axis of symmetry. What's the axis of symmetry? That means that a mirror image, the upper half is identical to the lower half. And the same story for the Y. So the Y is also an axis of symmetry. So if you have one axis of symmetry is sufficient, the product moment of inertia is going to be 0. And I put 0, okay, bold-faced like this to indicate that this is very important. And I include this as or I put it as in a form of a question. Okay, which of the following is true for a cross-sectional area has one axis of symmetry? So not necessarily to be 2, because this will give you 0 automatically. So the moment of inertia about the 2 axes of the area are equal, or the broad moment of inertia with respect to the 2 axes are same, or this is, or, so obviously the answer is D, where the product of inertia is 0. Friction. Friction is very important, and this is what is given. F is equal mu n, less than or equal mu n, where mu, they are using mu s. This is a coefficient of static friction. Because we have another one, it's called mu sub k, which is a kinematic coefficient of friction. Okay. So I need you to remember that the N is a normal force and F is a friction force. So if you look to this block here, let me put a block and try to. I don't know if I was able to send to you. I was really busy with a lot of things. So I don't know if I was able to send the recording or the link to the recording of the previous lecture or not. If not, I will send you the link to Google Drive where you can download the lecture and watch it again if you are interested. Or for those who missed it, probably you can watch it. So this is page 4 here. And I will do my best to scan this thing and send it to you. So if you do have a block resting on a surface like this, and we have an external force P. So this is an external force trying to push this block. The block has weight, W, and W is equal mg, by the way, mass times the gravity acceleration. We have a force here is called N, normal force, which is a reaction. And we have what is known as the friction force. This is F. He's using uppercase F. Some books they're using lowercase f, whatever the symbol that he's using is using upper. So the F is less than or equal mu S N. This is called the friction force. If the external force P is larger than the friction force, the block will slide. It's called the sliding. The block was here and it's going to slide, like the block I have from New Mexico when I was teaching back in Las Cruces in New Mexico. I still have it. I was telling my friends for the PE, this block came from Las Cruces in New Mexico. I have it. I still have it. Okay, and I was teaching there. So if this block here, here it is a block. Okay, so if this is external force, I am pushing with the here, and there is a friction between this block and the surface, in this case the paper. So if I'm able to push this block with external force, if my external force is greater, the friction force always opposing the motion, always. If this force is bigger, the block will start to move, as you can see. This is called sliding. But if the position of the external force at a different location, the block will not slide. The block will do what? Overturn. It's called overturning. Here it is. You can see overturning, overturning. So there are two situations that we look to when we examine the friction. It could be either sliding, sliding, ing. Here it is, sliding, or the block will rotate, which is overturn. It depends on the moment, and I will show it to you. So if this block, and this is a force here, the block may stay in the same place, but it will rotate like this. This is called rotation. Rotation. So we have sliding and we have rotation. In either case, you will find there is a friction force. Always we have, if this is a P, this is external force P, and again this is the weight, and also the normal force N, and the friction force F less than or equal mu sub S times N. And sometimes they have a tricky problems. I believe I have a bunch of them. I will be glad to send you some, because you have to examine both. You have to examine the sliding scenario and the rotation scenario in order to get it right. Okay. So the I have many problems here. Friction belt, screws, and okay, we're almost there. We're almost there, because the PE group, I told them that it joined me, and hopefully I will be able to finish the statics and move to the mechanics of materials. But it seems to me that. So again, the static equilibrium will occur as long as the force, the external force, okay, less than mu n, which is this is the friction force. okay? And N is a weight, which is a block. Here it is. This is W, and this is the normal force. The normal force is equal W. Normal, some forces in the y direction. And here are the scenarios that the block will move or block will stay in place, and so on. So we have something called impending motion, which is about to happen. They call it limiting friction based on the column friction and the motion, okay? And I mentioned mu sub k, by the way, which is called kinetic coefficient of friction. Kinetic coefficient of friction. Mu sub k is much smaller, about 70%, let's move it that way. Mu sub s. The kinetic coefficient of friction is a friction coefficient that will occur when the body starts to move. And you notice that when you have your car, or my car in this case, okay, and the battery is dead, okay, and I'm trying to push the car. It takes too much force from me, external force P, to push the car at the beginning. When the car starts to move and the wheels start to rotate, my force is getting less. Why? Because at the beginning was mu s. When the car starts to move, the coefficient of friction is equal mu sub k. But since mu sub k is less than mu sub s, which is about 70, so I will be able to keep pushing the car. So it takes too much force from me to overcome mu sub s, but the moment that the car starts to move, you will find that I need less force because the mu sub k is less than mu sub s. And there is a curve, if you remember, if you go to the statics book, you will find that the curves goes like this and they drop and continue like this. So this is a mu sub s here, and this is a mu sub k. Okay, so I needed to be aware of that. I have some problems here. I encourage you to go over them. One of them, for example, that the block in the figure A will, we have the angle, the friction angle phi is equal the inverse tan of mu sub s, by the way. I need you to know this. Okay? And I can show you this next time, as I have a presentation also. I used to show to the students, okay, when I was teaching the statics. I have different problems, but basically straightforward equations. Let me just jump here, and I will be glad to go over. Built friction is another section that listed in the NCEES, where you have a pulley, okay, and you have a belt around it. And in this case, if the belt is a frictionless with the pulley, okay, that means that the tension along the two sides are equal. But if we take the friction into consideration, which we should, so we are using this equation, where if this is F2 and this is F1, where F1 is equal to F2, and this is called the angle of contact, theta, the angle of contact theta. So this is the equation that F1 is equal F2 times E mu theta. Mu is the coefficient of static friction, mu sub k. So this is the equation that we should be aware of. I have a problem here, very interesting problem. Okay, mu sub s is given, and the block is 100 kilogram, and the slope of this plane is 30 degrees. Okay, there is a mass m here, and there is a tension. And he said that what is the maximum M that can support or can be supported by this system here. So right now this block is trying to slide along this plane, okay, but the mass M can hold this, and this is around this pulley here where we have coefficient. The angle of contact, by the way, you have to be careful, because the angle of contact in this case, like this, is a 90 degrees. Okay, the theta in the previous equation, okay, this angle theta is called the angle of contact, okay, and it must, by the way, expressed in radians, which is pi over 180. This is a conversion, and this is why you'll find that here it is, pi over 180. Okay, sorry, my solution here, this is a problem, by the way, problem 420, pi over 180. So you take whatever the angle is, the angle of contact, and you multiply it by pi over 180. This is the one we use it to convert from degrees to radians. Okay, is also another good problem. We're applying equilibrium equations and straightforward, and I'm sure that you will come up with questions. The screw thread is also another area where the moment is given by this equation, and all these parameters are given, the P and R and alpha and theta, all these things are defined for you. And I gave you some illustrations here, like the screw jack that we use it to raise our cars. We can raise much weight than our weight because of what? Because of this equation. We can raise it because we are using the friction, okay, and we are applying less force to raise much load as we do. So this is a problem 421. A clamp is used to hold two pieces of wood together as shown. The clamp has a double square thread. Okay, mean diameter is given, all the dimensions are given, the friction is given, and the maximum torque applied to tighten these clamps is given. So what will be the force that exerted into? So I'm applying a torque, and I need to get the force that will be applied or exerted on these two blocks. It is, if you look to the second page, you will find that. So since it is a double threaded, so the length is equal to times the pitch, and this is 2 times 2 is equal 4, and the angle, the lead angle, and we apply the equation and we can get the P. I repeated the same problem, and in this case I am asking for what is the torque required to loosen. So I know this is a lengthy one, but look at it and let me know if you have any question. Trusses, we covered it in depth, if I remember correctly last time. So trusses are covered very well, okay? And I hope that you understand all the problems in the trusses. And I believe at the end they added section about concurrent forces. Nothing really new. I have a problem here, very simple, how to find the force. And basically you're applying the two equilibrium equations since it's a concurrent force system. So in this case, we are applying the two equations because the moment equation is not applicable for a concurrent force system because there is no moment R. So look to this, it's another problem here also. If the vertical reaction is given to be 10P, okay, so it is a truss joint is given, and you have two members, and he was asking to find the force, the force in the two members. And also we need to know tension and compression. We need to understand this very well, and already I covered it last time. So these are the two tables, and I followed this by, no, the third table here is this, which is a continuation. And I have series of problems, additional statics, okay, practice problems. Please go over them. They are very interesting problems, and you are very welcome to ask me if there is any problem that you have a question related to it, or if you find a typo or anything that you want me to elaborate, I will be glad to do that. The following section, or the following chapter, is called Mechanics of Materials. Mechanics of Materials. And again, 7 to 11 questions. Statics was what? It was statics also, it was, no, statics was from 8 to 12. So the number of expected questions from 8 to 12, mechanics of materials. My favorite subject, the one I taught it for about many years. And I include this a lot in my PE books. So here are the topics: the shear moment diagrams, stresses and strains, deformation or deformations, combined stresses, a principal stress and Mohr circle, and finally elastic and plastic deformations. Those are the topics listed by the NCAAS. This is exactly verbatim from the NCAAS. The first thing that they provide, this is the first picture that you will see in the NCAAS, give you the stress strain curve. This is strain and this is stress. Strain is a dimensionless quantity, by the way, okay? But we're still using inch per inch or millimeter per millimeter. Or it could be expressed as a percent. And the stress here in PSI, pounds per square inch. And he showed you a stress strain curve for a material does not have a well-defined yield point. You'll find that this is the linear portion, which is a straight line. And after that, it has a curve. And so here we have what is known as the yield strength at 0.2%. You remember in this steel manual, or in the steel manual, we have two numbers, the F sub Y and F sub U. These are properties. Let me bring the steel manual show to you. It doesn't matter which edition you have. This is the 14th. Yeah, this is the 14th, yes. Right now they have the 15th as far as I know. So in the steel manual, there is in section 2 or part 2, okay, you will find that they provide us with tables. Let me see if I can find the tables very quick. I believe it's in part 2. Sometimes I forget the location of the stuff, but these tables, they have the tabulated values for the F sub Y. Here it is. These are the tables in the steel manual. Okay, they have what is known as F sub Y and F sub U. F sub Y, here it is. F sub Y is the minimum yield stress, and F sub U, let me get closer here, at least you can see it. If you are not familiar with the steel manual, don't worry, I'll show it to you when it is. F sub U, which is this number here, the tensile strength or tensile stress or strength, both of them are used. So for any kind of steel that you are going to use to design your structure, okay, A36 steel or whatever is, all these kinds of steels are available. And so these numbers, they came from the testing from the lab, okay, after they manufacture the steel with a certain composition, we test them. So one of them is called the offset method. This is called the offset method. Okay, where we move along the x-axis 0.2, this is 0.2%. The 0.2 here is 0.2%. Here it is. 0.2% means is 0.002. So I move along the axis 0.002, and I draw a line parallel to this. This will intercept with the stress strain curve. This number, the horizontal, I will draw a horizontal line. This is the F sub Y. This is called the yield stress using the offset method, So I need you to be aware of that, okay? So uniaxial stress strain, by the way, the word uniaxial, what's uniaxial? In the lab, and most of you remember this, specimen here. This is okay, where we screw the specimen to the testing machine and apply the axial load. Since the load is applied only in one direction, we call it uniaxial. Okay, so if this is a specimen here like this, okay, and we screw it to the testing machine and apply the load P, we call it uniaxial because the load is applied in one direction only. But if the material has a well-defined yield point, which we are going to see it later on, we are going to use the lower yield point as a criteria to determine what is the yield. Okay, so this is F sub Y. Okay, the F sub U, this is the ultimate. Okay, the tensile strength as we're going to see it. Okay, in the following diagrams. Okay, so I needed to be aware of that. I have some definitions here. Mechanics of materials deal with the determination of so and so. Materials under uniaxial stress, simple tension. We have something called modulus of elasticity, E. Modulus of elasticity is E, which is the slope of the linear portion, E. So E is equal sigma over epsilon, which we call it Hooke's law. Okay, but one of you has a question for me, probably, or a comment or a suggestion or a criticism. No problem. Don't worry too. Okay. Did you send chapter 6? I think I sent it, Carmelita. I sent it to you last time. I don't know, unless if you didn't receive it, I'll be glad to send it again. If you want me to send it again right now, I think I can send it to in 22 seconds. Yeah, it was sent. Okay, no problem. Okay, you are very welcome. It was sent, and any of you, since I know her email very quick, so I send it to her. I send it to the rest of the transportation group also, just in case. So any of you missing this, but I'm hoping that because my lawyer always advised me not to send any PDF, because in the past we have an issue with the PDF files that I send it out. So he told me that don't send it, but because I'm running out of time and I am late, I was hoping that I have the whole book ready for you guys in the 9 chapters. I hope I can get this very soon. I'm working very hard to try to get it, to wrap it up. But because the day has only 24 hours a day, so do you know who came up with the 24-hour clock? The Egyptians, which is I am one of them. So there are 24 hours a day only. There are 24 hours a day. So if the day is 28 hours or 30 hours would be great. But unfortunately, my grandfather, I wish that they made the day 30 hours. At least I would have enough time. But anyhow, it's too late right now. It's too late. So this one engineer was telling me, Dr. Mansour, your grandfather is a problem for everything. I told him why. He said that if I have 30 hours a day, I will be able to finish my study and taking care of the house and everything. Another engineer said, no, I am happy with the 24 hours because if the day is 30 hours, probably will work more. But the PE, I will pass the PE and it will be over. So, anyhow, so modulus of elasticity is the slope of the line, sigma over epsilon. The 0.2% offset is very important this to determine the yield strength if the material does not have a well-defined yield point. Okay, like for example, high carbon steel and mild steel, and as we're going to see. This is how we do the tension test. Okay, bro, they are showing a rectangular, but normally we are using circular member like this. You remember in mechanics of materials lab, we are pulling this, and I believe I have a specimen after failure. This is another size of a specimen. Okay, we are using their ASTM. Something's called ASTM, the American Society ASTM, the American Society for Testing and Materials. And this is after failure, by the way, after that complete tension test. So you'll find it's neck down, as you can see here. Okay, the smallest. Okay, and we measure the diameter after failure, and we determine the percent reduction in area and so on. So this is the repetition of what I just talked about, the offset method, which is a 0.2%, and stress is equal P over A. Stress is equal axial load divided by, or axial force divided by the perpendicular area. It must be perpendicular area, by the way, you have to be careful. Units are PSI or Pascal or megapascal. So units are important. And problem, this chapter has a lot of problems, by the way. So 6.1, which of the following is true for a material does not have a well-defined yield point, okay, of the stress-strain curve? That the design yield strength is taken as a lower yield point? No. The design yield strength is taken as a upper lower? No. Okay, the design yield strength is determined by using 0.2% offset. This is yes, 0.2%. Okay. Okay, the design yield is determined by 0.002%. No, it is 0.2%. If he get rid of the percent here, the answer will be yes. You have to be careful. 1 0 can make a difference. Okay, so the answer is C, and here it is. Sometimes, by the way, I change these things. So if you find this doesn't match the correct answer, please let me know. If you look to this, you have two rods with variable cross sections, as you can see, but they are restrained at both ends. So a steel rod is fixed, and they give you a lot of properties about the length and the modulus of elasticity and the area and so on. But the question is, this rod is what? Is statically determined or statically indeterminate to the first degree, or statically indeterminate to the second degree, or the third degree? If you remember, this is a 2D system, by the way. This is X and Y, and this is 2D. Since 2D, so how many unknowns I have here? Do you remember the fixed end? Any fixed end, okay, it does have 3 unknowns. A sub y, if this is the end A, and this is A sub x, and this is the moment, M sub n. So we have 3 unknowns here. So I have 3, and the 3 here are 6. So are 6 unknowns. But I do have 3 equilibrium equations, which is basically the sigma force x, sigma force y, sigma moment. Here it is. And we don't have any conditional equations. I will talk about conditional equations later on. Okay, what does it mean by a conditional equation? So basically, this is 3. So the difference between the unknown and the number of available equations, and if any conditional equation exists or not, we ended with 3. So this here is statically indeterminate to the third degree, and the answer is D. And we're going to see more. If you flip the page, you'll find the definitions given in the NCEES, all this NCEES FE reference book, that epsilon, which is a strain, is equal delta L over L sub O. L sub O is the original length. The original length. They are using L sub O. So strain is equal delta L, which is a change in length, percent elongation is given, is delta L over L sub O. That's given by this equation. And we have an equation also for reduction of area after the specimen failed, we determine the final diameter, and from the final diameter we can get the final cross-sectional area, and we are using this equation here to get the percent reduction in area, which is AI is the initial area, and A sub F is the final area divided by the initial times 100, make it shear strain. Shear strain, we are using the letter gamma. Gamma is equal tau divided by G, where tau is the shear stress and G is called shear modulus. We're going to see it in the torsion. Do you remember the equation I told you? Theta is equal TL divided by JG. This is the G. This is the shear modulus. Okay? Or there is another equation, tau is equal TR divided by G. No, TR, no. This equation is not correct. TR divided by J. Sorry, it seems to me that TR divided by J. Yes. This is the G, the shear modulus. The shear modulus is a constant in the torsion. We're going to see the torsion test. And this is an equation, very important equation. This is correlating the G shear modulus to modulus of velocity and Poisson's ratio. This Greek letter is called nu. This Greek letter is called nu. If you'd like to remember it, here it is, nu. Okay? Poisson's ratio. And this y, by the way, you'll find G, by the way, is about 40% of E. And in the, as we saw, some tables are provided in the end of the statics section. You will find also tables are provided in the mechanics of materials. Let me show it to you. I don't know if I have it or not. I believe I have it. Yeah, here it is. Also, they have these tables here. There are two tables related to, and this is on page 60, by the way, of my book, but in the original book, let me get the original book, the NCEES. This second. This is the NCEES, the FE reference 10.0. So if you go to mechanics of materials, where is mechanics of materials? Let me see if I can get it for you guys. Yeah, here it is. So this is what we started, mechanics of materials. This is on page 130 of this book. As I told you, this book, they made it, okay, one column per page, so the number of pages has been, so this is what I follow. This is what we just talked about, the offset method, the 0.2% offset. You'll find all these definitions and so on. So, and we are here right now. This is the equation I just mentioned. So I'm just follow the book by taking these equations and talk about it. At the end, you'll find series of tables, and here they are. This is a table number 1, material properties. Okay, and this is a table number 2. Okay, average mechanical properties of typical engineering materials. And you will find that, for example, let's come to steel. This is aluminum steel. For the modulus of velocity E, for example, here is, let me see if I can get it bigger for you guys. I know the print is so small. Forgive me for that. So if you look to this is 29. 29 what? 29 10 to the 3 KSI, which is a modulus of velocity for steel. Okay, so steel is, we have one number. Okay, normally we use is a 29 million. Okay, PSI. or 29,000 KSI. If you look to the number next to it, which is G, which is this one here, modulus of rigidity G, or the shear modulus. It has three names. This G, by the way, it has three names. Modulus of rigidity. This is, so if you take the 11 and 29, this will give you about 40%. 11, 29 divided 38%, okay, or 0.379. So it is about 40%, okay, because the modulus of elasticity, okay, is much higher, and the Poisson's ratio, we're going to see some, I don't know, does he have some numbers for Poisson's ratio? Poisson's ratio for steel, we are using 0.3, here it is, Poisson's ratio 0.32, here it is, 0.32. So Poisson, and on the same table, by the way, the table 2, if you, and this is on page 139. And probably in the future, I will refer you to the document here. At least you can follow, because you need to know exactly, because this is the only thing that you are going to see on the exam, as I mentioned before many times. So it will be a good idea. For example, the statics, okay, the one we covered, okay, we talked about all this stuff, and where is this is statics, here it is. Yes, so I will be glad to just to walk you through, and the two tables I was referring to or the tables at the end of the statics section, here it is. This is the rectangular section I was talking about, which is a BH cube divided by 12. Sorry, and the BH cube divided by 3. Do you remember? We use the Parallex Theorem, and we need to know that. Okay, so what I'm providing here, it is based on the NCEES, and so the G and E are important. And let me go back again. I need to wrap up something very quick, because I need to stop, because it seems to me that I will not be able to continue beyond that, because I'm really, really hungry. I'm fasting, by the way, so pray for me. After Ramadan, probably I will be able to. Okay. So, anyhow. So this G, we were here, by the way. I am back on my book, and this is page 4, by the way, page 4 of my book. I number each chapter from 1 until I assemble all of them, and hopefully one day you will get all the 9 chapters, and one day probably, if I'm able to finish the entire book, will be available, okay, later on. So the G is equal to E divided by 2 times 1 plus nu, where nu is called Poisson's ratio. Poisson's ratio, by the way, is given by this definition, which is a lateral strain over axial strain. Lateral strain over longitudinal or axial, by the way. Okay. Let me tell you something, which I show this to the students, because there are 2 types of strain we're going to see. When a member, okay, if this rubber band like this, okay, subjected to axial load, uniaxial, means that I'm pulling this way. So the rubber band, if you mark 2 points along this rubber band before we start, and this is what we do in the lab, by the way, but we use steel. Let me mark two marks here. Okay, so those are the 2 marks, okay, before I apply the load. Now I'm pulling, so these 2 points will get apart, away from each other, because they will stretch. So there is an axial strain, but also at the same time, the rubber band is getting skinnier and skinnier and skinnier. So there are 2 types of strain: axial strain, which is longitudinal, and lateral strain. The lateral strain is very small, by the way, compared to the longitudinal strain. This is why Poisson's ratio nu, you will find nu, okay, Poisson's ratio, nu, I believe I mentioned it somewhere here. It is between 1/3 and 1/6. For most structural materials, for steel, for example, is 0.32. Poisson's ratio for steel is equal 0.32. Some books they are using 0.33. Okay. Poisson's ratio for concrete, by the way, concrete is not constant. It could be 0.17, okay, to about, okay, 0.24, something like that. And there is a professor, his name is Timoshenko. He's a Russian scientist. He immigrated to the United States, and he was a professor at Stanford, by the way. He's a very famous professor. His name is Timoshenko. He authored about 6 or 7 books, and these books are still, by the way, nobody can find even a little tiny mistake or an error. Even he authored all these books way back before the computers are widely used or available as we see nowadays. So anyhow, so Timoshenko came up with the equation that the Poisson's ratio for concrete, it is a square root of F sub C prime divided by 350. And we're going to see F sub C prime, by the way. F sub C prime is a 28-day compressive strength for concrete, which is B over A. So if you put this as an average value about 4,000, just for the sake of discussion, so 4,000, if you take 4,000 and you take square root, would give you what? Square root, and you divide this by 350 divided, it give you 0.18. 0.18. So 4,000 PSI is this very common concrete. We use it on a daily basis. Sometimes we use 5,000 for bridges, okay, which is about 6 sac mix. We're going to see that. 6 sac mix, okay. And as all of you know, a sack of cement, how much it weighs, by the way? How many pounds in a sack of cement? A sack of, do you remember? They made it 94 pounds per sack. Why they made it 94, not 100 pounds? Oh, because it will be much easier to carry, maybe. Oh, as one engineer was joking with me when I asked them, why 94 pounds? Why they don't make it 100 pounds, at least easy to remember? Okay, we will see this later on. And now, so the concrete strength F sub C prime, it depends on the how many sacks of cement that we add, and we're going to talk about mixing of concrete, and you will enjoy a lot. I will teach you the mixing of concrete so you can prepare your own mix, and you don't have to go and buy any concrete from anybody. You are going to mix it. Okay. So if you look to the, I'm still here on, so the strain, engineering strain is equal delta L over L sub O, as given here. Here it is, the elongation. Okay, delta L over L sub O, or strain. I have a problem here to illustrate, a figure here to illustrate what is meant by axial deformation, that the member was originally L, but because we are applying a tensile force, so delta L, and the word engineering is used here because we have something called the true stress and the engineering stress, and you're going to see the difference between them, and you see which one is larger. Okay, so the steel rod shown here, it's fixed at this end here, and the free at the other end. And we have two forces. We have P1 and P2. The cross-sectional area is given for each, and is asking what is the engineering strain at point A. Point A, this fixed end. So this A here, it will not move. The elongation will be happening along the member, but this point A is a fixed end, and this Y, A is located at the fixed end built in. Therefore, the strain is 0 at this point. We always assume that the strain and also another term, we are going to see it later on, is called slope, theta, 0. So the deformation and the slope at the fixed end must be 0. Percent elongation, it could be determined as the percent reduction area or percent elongation over the length. Here are the equations. And the percent reduction in area, the one we saw, it is the initial area minus the final area over the initial area times 100. And I have a problem for you, problem 6.4. I have this steel rod, fixed end, and the areas are given. And what is the percent elongation of the portion AB? So this is AB and this is BC. And there is a force here, P. And the P is given how much? Applied force of 8 kips. So this is equal 8 kips. How much the percent elongation? Because due to this external force pulling this member, so the member will stretch. We have the modulus of velocity E, by the way, which we said that it is sigma over epsilon. Sigma, which is the stress, is equal P over A. And epsilon is equal delta L over L. If from this, we can get what is known, and here it is, by the way, I did it here for you. So the delta can be expressed as PL over AE. This is a very important equation. Delta is equal PL over AE. The deformation or the elongation, deformation or elongation, both of them are acceptable. And this is Hooke's law. Do you remember Hooke's law? Professor Hooke. So first I determine what is delta. I got this, how many inches? And since I know the length, which is 24 inch originally, so the percent elongation is equal the axial elongation over the original length. So it is delta L over L, and I get it as a percent, and this is why we picked one of these correct answer here. So this is a very good problem. This, it could be a target for a problem on the exam, but we should know how, what are the given information always. And here it say that ignore the member weight. And I will show how to calculate the weight if the weight should be considered. Because the weight is equal volume times density. All of us, we know gamma water is 62.4 pounds per cubic foot. So if you have 1 cubic foot of water, it weighs 62.4. What do you think about gamma steel? Is the steel heavier than water or lighter than water? Much heavier than water. Have you ever seen somebody throw a steel bar over on a surface of water? Will sink or will float? It will sink, because gamma steel is, so if the water is 62.4, what do you think about gamma steel? Can you guess? How many pounds per cubic foot? If you have 1 cubic foot of water, it weighs 62.4. This is at normal temperature, by the way. But what do you think about gamma steel? Gamma steel, I need you to remember that it's 490 pounds per cubic foot. And we're going to see it later on. Okay? I will stop here because I think I am really get tired, and we'll start here next time and we'll continue our discussion. Enjoy the rest of your day. I will do my best to help you guys, to keep helping you. Just pray for me to stay healthy, and I pray for you to stay healthy, and we will continue our discussion. Hopefully that I can help you to pass this FE, and after that you'll get your PE, and after that you'll get your SE, and all these letters are very useful. Okay, thank you very much. Good night, everybody.